Right, the first of two parts. Using triple integration to find the volume of a sphere, first of all using Cartesian coordinates, and then probably in a separate video after this, because it'll probably take too long, using spherical coordinates. With Cartesian coordinates, the easy part is that each little volume elements that you're going to be adding up will just be nice little cubes. We take our standard three-dimensional set of axes, x, y and z. I've not drawn the parts before, just considering the first octant, so that we're looking down into a corner where the xy plane would be the floor, z equals 0. The xz plane, that's y equals 0, would be the side wall, and the yz plane, x equals 0, is the back wall. Looking down into that corner with Cartesian coordinates, you can locate any little volume element simply by going along a certain distance x, in a certain distance y, and then coming up a certain distance to find our little box. A little cube sitting in space. And to find the volume of something, we just rush around gathering up all these little boxes until we've got the whole lot, or as many as we need. And the size of each little box is simple enough in Cartesian coordinates, because the distance this way would just be the small change in x, the distance that way would be the small change in y, and the distance up the way would be the small distance in z, which means that the volume element would just be the product of those three. So that if I wanted to work out the volume of some region, I would simply rush through the region, gathering up all the little volume elements. I would rush through the region, gathering up the dx, the dy and the dz. Now for this one, for a sphere, again if I just take the first quarter here, then the sphere would form a circle in that wall, on the floor, a portion of a circle there, and then a portion of a circle in the back wall. That would be 1/8 of the sphere, where its equation is x squared plus y squared plus z squared equals 1, just for simplicity. I could call it more than that, I could call that r. Why not just call it r? So we'll make it equals r squared. So the circle on the horizontal plane, where z is 0, that circle will have equation x squared plus y squared equals r squared. Whereas the shell, the roof of it all, is going to have this equation here. Then to gather up each of these little boxes, and for the sake of working at the volume, each of these little boxes will be empty. If I wanted to gather up the value of some function operating within the volume of the sphere, then each of these little boxes would have some value attached to it, and then I'd rush around gathering them all up. Essentially I'm gathering up empty boxes. I'll not be using any function, I won't be evaluating a function apart from the trivial one of 1. And the way you would do it would just be to, first of all, decide which way you want to stack them. If we went along the y direction and gathered the little boxes, but first of all stacked them up until they hit the ceiling at little columns. So that'd be the first stacking, stack them up in the z direction, then go through it gathering them up in the y direction, so that eventually I would end up with this thin wedge. And then lastly gather them up in the x direction, gather all the wedges together, and that way I'd collected all the boxes, collected all the volume elements. So that would be first of all z. Z would start at 0 and go up until it hit the roof. Rearranging that equation, that means it would go up to the square root of r squared minus x squared minus y squared. Once I'd gathered up the z's, I'll start collecting these columns along the way in the y direction. So the y direction is easy, it's going to start at 0 until it hits this circle. So for that circle, I'm going to have y would be equal to, at its far end, r squared minus x squared. And then once I had those thin sheets, I'd gather them up across the x direction, but that'd be the easy one, because I'm just going to go from 0 to r. R being the radius of the circle, since its centre's at the origin. Meaning that the volume of the whole sphere should be, again, That's only 1/8 of it, because I'm just sitting in the first octant, keeping everything nice and positive. No negatives allowed in there. It'll be 8 times the volume of that octant. That would be 8 times the volume of the octant taking x from 0 to r, y from 0 to the square root of r squared minus x squared, and then z from 0 to the square root of r squared minus x squared minus y squared, dx, dy, dz. What remains now is simply to evaluate that part. Start at the top. I'm going to take a wee bit of doing, and that's why you go for spherical coordinates with these. So the first part would be this. So I've got the volume of the whole thing is going to be 8. I'll take this nested form out and iterate it out sideways. So I'm going to have from 0 to r dx, from 0 to r squared minus x squared dy, and from 0 to r squared minus x squared minus y squared dz. Takes away from here. That's it spread out. Some of them might contain parts that could fall into the others, they might not quite be constants. We'll get them one at a time. So I've got 8 times. Now this first one, that's simply one lot of z. So when I integrate that, that'll just be z, evaluated at this and then that, which means it'll just come out as the square root of r squared minus x squared minus y squared dy. And yes, I know, because it was just a 1 in front of the z, then that initial column could just been considered a run through the y's, and you could have just had a double integral. That's all it's ended up with. But for this part, integrating with respect to y, so x is a constant as far as it's concerned, so we end up with this thing to integrate. But that's that familiar little pal, a squared minus y squared, where immediately you think, put in a trig. Because if I've got a sine squared, something minus sine squared will be cos squared, root cos squared cos, all the nasty stuff gone. So do that substitution. Let y equal, I'll have to part with that, the square root of r squared minus x squared sine theta. So that dy by d theta will be the derivative of that. That's just a constant. Oops. Cos theta. Change the limits. Missed one out. If y equals 0, then theta just equals 0. And if y equals that, r squared minus x squared, well, that's the same as that times, so that means that root r squared minus x squared sine theta just equals root r squared minus x squared. That's a bit nasty to the side. So sine theta equals 1, I'm going to rub this out in a minute. So theta equals pi upon 2, which means I've got 8 times the integral from 0 to r dx. That's the gathering up of the x's. Remember that part? Ooh, that's not too so good. That's the gathering of the x's that way. What I'm doing just now is I'm gathering my stacks up in the y direction. So I've got from 0 to pi upon 2 of this thing, which is going to be the square root of, and we could just assume the tidied up version, but it's going to be r squared minus x squared sine squared theta times, I'll have to lose you, I'm afraid, cos theta d theta with that little r squared minus x squared that I missed out putting in. So I've got from 0 to r dx of, now how much tidying up do I need to do here? That's a common factor, that's going to come out, it's going to come out the square root and leave it as r squared minus x, square root of r squared minus x squared. Inside the square root without, I'm going to have 1 minus sine squared, that's cos squared. Square root of cos squared will just be cos. Times the same thing again, r squared minus x squared cos theta d theta. I'll take this up to the top, sorry about this, which now means I've got the volume equals 8 times the integral from 0 to r, but that's a constant as far as theta is concerned, So that part could come out, and it's the square root times the square root, so it's going to be r squared minus x squared dx times the integral from 0 to pi upon 2 of cos squared theta d theta. Take this line out. And yes, you could use a wee beta function there, just to form a little fraction and get rid of that straight away. But since we've got the trig things out to play, let's let them play a little bit longer. Cos squared theta, you can get that rearranged back to a linear function of theta just by using the double angle formula. So that for cos squared theta, I could rearrange that to be cos squared theta equals a half of 1 plus cos 2 theta. There's a half, I can take that out, so that's that, dropped that down to 4 now. So I've got 0 to r, and yes, I could have worked this part out independently of the theta one because they don't share anything in common. And here, instead of that, I'm going to have 1 plus cos 2 theta d theta. Getting there, pretty tedious. Just think how fast that can be done just with a single integration of a disk running along the x-axis. But it's the principle of that triple integration. So I've got 4 times, well, I think we'll just do them both at the same time now. So the first one is going to come out as r squared x. R squared is just a constant, so it goes back to that. X squared will go up to power 3, so that's 1/3 x to the power 3, evaluated from 0 to r. Independent of this one, 1 will go back to theta, cos will go back to a half sine 2 theta, don't forget to divide by the derivative, evaluated from 0 to pi upon 2. So I've got 4 times. Much space have I got here? When that goes, the zeros we can forget about. When r goes in, I've got r cubed minus 1/3 of r cubed, so that means I've got 2/3 of r cubed. This part, theta, is going to be pi upon 2. Sine 2 theta, that's the same as sine pi. Sine pi, that's 0. Minus 0 minus sine 0 is 0, so that's just pi upon 2. So altogether, I've got 2 into 2 cancels out. I've got 4 upon 3 pi r cubed. A fairly lengthy process. So compare that then to doing the same thing, the triple integration using spherical coordinates. So we'll do that in the next video clip. So hold your breath.